Hello students, in this chapter atoms, we are going to study about the alpha particle scattering and Rutherford's nuclear model of the atom. Next we are also going to study about the atomic spectra and Bohr model of the hydrogen atom, and also about the line spectra of the hydrogen atom, and the next one is about
Atoms. Introduction. By the 19th century, enough evidence had accumulated in favor of atomic hypothesis of matter. In 1897, the experiments on electric discharge through gases carried out by the English physicist J. Thomson revealed that atoms of different elements contain negatively charged constituents, electrons, that are identical for all atoms. However, atoms on a whole are electrically neutral. Therefore, an atom must also contain some positive charge to neutralize the negative charge of the electrons. But what is the arrangement of the positive charge and the electrons inside the atom? In other words, what is the structure of an atom? The first model of atom was proposed by J. Thomson in 1898. According to this model, the positive charge of the atom is uniformly distributed throughout the volume of the atom and the negatively charged electrons are embedded in it like seeds in a watermelon. This model was picturesquely called plum pudding model of the atom. However, subsequent studies on atoms, as described in this chapter, showed that the distribution of the electrons and positive charges are very different from that proposed in this model. We know that condensed matter, solids and liquids, and dense gases at all temperatures emit electromagnetic radiation in which a continuous distribution of several wavelengths is present, though with different intensities. This radiation is considered to be due to oscillations of atoms and molecules, governed by the interaction of each atom or molecule with its neighbors. In contrast, light emitted from rarefied gases heated in a flame, or excited electrically in a glow tube such as the familiar neon sign or mercury vapor light has only certain discrete wavelengths. The spectrum appears as a series of bright lines. In such gases, the average spacing between atoms is large. Hence, the radiation emitted can be considered due to individual atoms rather than because of interactions between atoms or molecules. In the early 19th century it was also established that each element is associated with a characteristic spectrum of radiation. For example, hydrogen always gives a set of lines with fixed relative position between the lines. This fact suggested an intimate relationship between the internal structure of an atom and the spectrum of radiation emitted by it. In 1885, Johann Jakob Balmer obtained a simple empirical formula which gave the wavelengths of a group of lines emitted by atomic hydrogen. Since hydrogen is simplest of the elements known, we shall consider its spectrum in detail in this chapter. Ernst Rutherford, a former research student of J. Thomson, was engaged in experiments on alpha particles emitted by some radioactive elements. In 1906, he proposed a classic experiment of scattering of these alpha particles by atoms to investigate the atomic structure. This experiment was later performed around 1911 by Hans Geiger and Ernst Marsden. The explanation of the results led to the birth of Rutherford's planetary model of atom, also called the nuclear model of the atom. According to this, the entire positive charge and most of the mass of the atom is concentrated in a small volume called the nucleus, with electrons revolving around the nucleus just as planets revolve around the sun. Rutherford's nuclear model was a major step towards how we see the atom today. However, it could not explain why atoms emit light of only discrete wavelengths. How could an atom as simple as hydrogen, consisting of a single electron and a single proton, emit a complex spectrum of specific wavelengths? In the classical picture of an atom, the electron revolves round the nucleus much like the way a planet revolves round the sun. However, we shall see that there are some serious difficulties in accepting such a model. Alpha particle scattering and Rutherford's nuclear model of atom. At the suggestion of Ernst Rutherford, in 1911, H. Geiger and E. Marsden performed some experiments. In one of their experiments, as shown in figure 12.1.
Hi, I am Ernst Rutherford. I did pioneering work on radioactive radiation. I discovered alpha and beta rays. I also created the modern theory of radioactivity by the alpha particle scattering experiment. I discovered the atomic nucleus, proposed planetary model.
They directed a beam of 5.5 MeV alpha particles emitted from a bismuth radioactive source at a thin metal foil made of gold. Figure 12.2 shows a schematic diagram of this experiment. Alpha particles emitted by a bismuth radioactive source were collimated into a narrow beam by their passage through lead bricks. The beam was allowed to fall on a thin foil of gold of thickness 2.1 times 10⁻⁷ meters. The scattered alpha particles were observed through a rotatable detector consisting of zinc sulfide screen and a microscope. The scattered alpha particles on striking the screen produced brief light flashes or scintillations. These flashes may be viewed through a microscope, and the distribution of the number of scattered particles may be studied as a function of angle of scattering. A typical graph of the total number of alpha particles scattered at different angles, in a given interval of time, is shown in figure 12.3. The dots in this figure represent the data points, and the solid curve is the theoretical prediction based on the assumption that the target atom has a small, dense, positively charged nucleus. Many of the alpha particles pass through the foil. It means that they do not suffer any collisions. Only about 0.14% of the incident alpha particles scatter by more than 1 degree, and about 1 in 8,000 deflect by more than 90 degrees. Rutherford argued that, to deflect the alpha particle backwards, it must experience a large repulsive force. This force could be provided if the greater part of the mass of the atom and its positive charge were concentrated tightly at its center. Then the incoming alpha particle could get very close to the positive charge without penetrating it, and such a close encounter would result in a large deflection. This agreement supported the hypothesis of the nuclear atom. This is why Rutherford is credited with the discovery of the nucleus. In Rutherford's nuclear model of the atom, the entire positive charge and most of the mass of the atom are concentrated in the nucleus, with the electrons some distance away. The electrons would be moving in orbits about the nucleus just as the planets do around the Sun. Rutherford's experiments suggested the size of the nucleus to be about 10⁻⁻15 meters to 10⁻⁻14 meters. From kinetic theory, the size of an atom was known to be 10⁻10 meters, about 10,000 to 100,000 times larger than the size of the nucleus. Thus, the electrons would seem to be at a distance from the nucleus of about 10,000 to 100,000 times the size of the nucleus itself. Thus, most of an atom is empty space. With the atom being largely empty space, it is easy to see why most alpha particles go right through a thin metal foil. However, when alpha particle happens to come near a nucleus, the intense electric field there scatters it through a large angle. The atomic electrons, being so light, do not appreciably affect the alpha particles. The scattering data shown in figure 12.3 can be analyzed by employing Rutherford's nuclear model of the atom. As the gold foil is very thin, it can be assumed that alpha particles will suffer not more than one scattering during their passage through it. Therefore, computation of the trajectory of an alpha particle scattered by a single nucleus is enough. Alpha particles are nuclei of helium atoms and, therefore, carry 2 units, 2e, of positive charge and have the mass of the helium atom. The charge of the gold nucleus is Z, where Z is the atomic number of the atom. For gold Z equals 79. Since the nucleus of gold is about 50 times heavier than an alpha particle, it is reasonable to assume that it remains stationary throughout the scattering process. Under these assumptions, the trajectory of an alpha particle can be computed employing Newton's second law of motion and the Coulomb's law for electrostatic force of repulsion between the alpha particle and the positively charged nucleus. The magnitude of this force is given by the equation 12.1, where r is the distance between the alpha particle and the nucleus. The force is directed along the line joining the alpha particle and the nucleus. The magnitude and direction of the force on an alpha particle continuously changes as it approaches the nucleus and recedes away from it. Alpha particle trajectory. The trajectory traced by an alpha particle depends on the impact parameter, b of collision. The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus, figure 12.4. A given beam of alpha particles has a distribution of impact parameters b, so that the beam is scattered in various directions with different probabilities. In a beam, all particles have nearly same kinetic energy. It is seen that an alpha particle close to the nucleus, small impact parameter, suffers large scattering. In case of head-on collision, the impact parameter is minimum and the alpha particle rebounds back, as theta is approximately equal to pi. For a large impact parameter, the alpha particle goes nearly undeviated and has a small deflection, theta is approximately equal to 0. The fact that only a small fraction of the number of incident particles rebound back indicates that the number of alpha particles undergoing head-on collision is small. This, in turn, implies that the mass and positive charge of the atom is concentrated in a small volume. Rutherford scattering, therefore, is a powerful way to determine an upper limit to the size of the nucleus. Electron orbits. The Rutherford nuclear model of the atom, which involves classical concepts, pictures the atom as an electrically neutral sphere consisting of a very small, massive and positively charged nucleus at the center surrounded by the revolving electrons in their respective dynamically stable orbits. The electrostatic force of attraction, Phi, between the revolving electrons and the nucleus provides the requisite centripetal force, Fc, to keep them in their orbits. Thus, for a dynamically stable orbit in a hydrogen atom, Phi equals Fc, so we get the equation 12.2. Thus the relation between the orbit radius and the electron velocity is given by the equation 12.3. The kinetic energy, K, and electrostatic potential energy, U, of the electron in hydrogen atom are given by the following equation. The negative sign in U signifies that the electrostatic force is in the -r direction. Thus the total energy E of the electron in a hydrogen atom is given by the equation 12.4. The total energy of the electron is negative. This implies the fact that the electron is bound to the nucleus. If E were positive, an electron will not follow a closed orbit around the nucleus. Atomic spectra. As mentioned in section 12.1, each element has a characteristic spectrum of radiation, which it emits. When an atomic gas or vapor is excited at low pressure, usually by passing an electric current through it, the emitted radiation has a spectrum which contains certain specific wavelengths only. A spectrum of this kind is termed as emission line spectrum. It consists of bright lines on a dark background. The spectrum emitted by atomic hydrogen is shown in figure 12.5. Study of emission line spectra of a material can therefore serve as a type of fingerprint for identification of the gas. When white light passes through a gas and we analyze the transmitted light using a spectrometer, we find some dark lines in the spectrum. These dark lines correspond precisely to those wavelengths which were found in the emission line spectrum of the gas. This is called the absorption spectrum of the material of the gas. Bohr model of the hydrogen atom. The model of the atom proposed by Rutherford assumes that the atom, consisting of a central nucleus and revolving electron, is stable much like Sun-planet system, which the model imitates. However, there are some fundamental differences between the two situations. While the planetary system is held by gravitational force, the nucleus electron system, being charged objects, interact by Coulomb's law of force. We know that an object which moves in a circle is being constantly accelerated, the acceleration being centripetal in nature. According to classical electromagnetic theory, an accelerating charged particle emits radiation in the form of electromagnetic waves. The energy of an accelerating electron should therefore continuously decrease. The electron would spiral inward and eventually fall into the nucleus. Thus, such an atom cannot be stable. Further, according to the classical electromagnetic theory, the frequency of the electromagnetic waves emitted by the revolving electrons is equal to the frequency of revolution. As the electrons spiral inwards, their angular velocities and hence their frequencies would change continuously, and so will the frequency of the light emitted. Thus, they would emit a continuous spectrum, in contradiction to the line spectrum actually observed. Clearly, Rutherford model tells only a part of the story, implying that the classical ideas are not sufficient to explain the atomic structure. It was Niels Bohr who made certain modifications in this model by adding the ideas of the newly developing quantum hypothesis. Niels Bohr studied in Rutherford's laboratory for several months in 1912, and he was convinced about the validity of Rutherford nuclear model. Faced with the dilemma as discussed above, Bohr, in 1913, concluded that in spite of the success of electromagnetic theory in explaining large-scale phenomena, it could not be applied to the processes at the atomic scale. It became clear that a fairly radical departure from the established principles of classical mechanics and electromagnetism would be needed to understand the structure of atoms and the relation of atomic structure to atomic spectra. Bohr combined classical and early quantum concepts and gave his theory in the form of three postulates. These are: Bohr's first postulate was that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy, contrary to the predictions of electromagnetic theory. According to this postulate, each atom has certain definite stable states in which it can exist.
My first postulate is that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy. And the second postulate is that an electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h by 2 pi. The third postulate is that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy, emitting a photon having energy equal to the difference of energy between initial and final states.
And each possible state has definite total energy. These are called the stationary states of the atom. Bohr's second postulate defines these stable orbits. This postulate states that the electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h by 2 pi. H is the Planck's constant, which is equal to 6.6 into 10 power minus 34 joules second. Thus, the angular momentum L of the orbiting electron is quantized, that is, L is equal to nh by 2 pi. Bohr's third postulate incorporated into atomic theory the early quantum concepts that had been developed by Planck and Einstein. It states that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy. When it does so, a photon is emitted having energy equal to the energy difference between the initial and final states. The frequency of the emitted photon is then given by h nu equal to Ei minus Ef, where Ei and Ef are the energies of the initial and final states, and Ei is greater than Ef. For a hydrogen atom, the equation 12.4 gives the expression to determine the energies of different energy states. But then this equation requires the radius r of the electron orbit. To calculate r, Bohr's second postulate about the angular momentum of the electron, the quantization condition, is used. The radius of n possible orbit thus found is Rn equal to n square by m into h by 2 pi the whole square into 4 pi epsilon naught by E square. The total energy of the electron in the stationary states of the hydrogen atom can be obtained by substituting the value of orbital radius in the equation 12.4 as En equal to minus E square by 8 pi epsilon naught m by n square 2 pi by h the whole square E square by 4 pi epsilon naught, or En equal to minus me power 4 by 8 n square epsilon naught square h square. Substituting the values, the equation 12.8 yields En equal to minus 2.18 into 10 power minus 18 by n square joule. Atomic energies are often expressed in electron volts rather than joules. Since 1 electron volt equal to 1.6 into 10 power minus 19 joule, the equation 12.9 can be rewritten as En equal to minus 13.6 by n square electron volt. The negative sign of the total energy of an electron moving in an orbit means that the electron is bound with the nucleus. Energy will thus be required to remove the electron from the hydrogen atom to a distance infinitely far away from its nucleus or proton in the hydrogen atom.
Energy levels. The energy of an atom is the least, largest negative value when its electron is revolving in an orbit closest to the nucleus, that is the one for which n equals 1. For n equals 2, 3, the absolute value of the energy E is smaller, hence the energy is progressively larger in the outer orbits. The lowest state of the atom, called the ground state, is that of the lowest energy, with the electron revolving in the orbit of smallest radius, the Bohr radius, a 0. The energy of this state, n equals 1, E1 is minus 13.6 electron volts. Therefore, the minimum energy required to free the electron from the ground state of the hydrogen atom is 13.6 electron volts. It is called the ionization energy of the hydrogen atom. This prediction of the Bohr's model is in excellent agreement with the experimental value of ionization energy. At room temperature, most of the hydrogen atoms are in ground state. When a hydrogen atom receives energy by processes such as electron collisions, the atom may acquire sufficient energy to raise the electron to higher energy states. The atom is then said to be in an excited state. From equation 12.10 for n equals 2, the energy E2 is minus 3.40 electron volts. It means that the energy required to excite an electron in hydrogen atom to its first excited state is an energy equal to E2 minus E1 equals minus 3.40 electron volts minus of minus 13.6 electron volts equals 10.2 electron volts. Similarly, E3 equals minus 1.51 electron volts and E3 minus E1 equals 12.09 electron volts, or to excite the hydrogen atom from its ground state, n equals 1, to second excited state, n equals 3, 12.09 electron volts energy is required, and so on. From these excited states the electron can then fall back to a state of lower energy, emitting a photon in the process. Thus, as the excitation of hydrogen atom increases, that is as n increases, the value of minimum energy required to free the electron from the excited atom decreases. The energy level diagram for the stationary states of a hydrogen atom, computed from equation 12.10, is given in figure 12.7. The principal quantum number n labels the stationary states in the ascending order of energy. In this diagram, the highest energy state corresponds to n equals in EQ 12.10, and has an energy of 0 electron volts. This is the energy of the atom when the electron is completely removed, R equals, from the nucleus and is at rest. Observe how the energies of the excited states come closer and closer together as n increases. The line spectra of the hydrogen atom. According to the third postulate of Bohr's model, when an atom makes a transition from the higher energy state with quantum number Ni to the lower energy state with quantum number Nf less than Ni, the difference of energy is carried away by a photon of frequency nu such that h nu equals E Ni minus E Nf. Since both Nf and Ni are integers, this immediately shows that in transitions between different atomic levels, light is radiated in various discrete frequencies. The various lines in the atomic spectra are produced when electrons jump from higher energy state to a lower energy state and photons are emitted. These spectral lines are called emission lines. But when an atom absorbs a photon that has precisely the same energy needed by the electron in a lower energy state to make transitions to a higher energy state, the process is called absorption. Thus if photons with a continuous range of frequencies pass through a rarefied gas and then are analyzed with a spectrometer, a series of dark spectral absorption lines appear in the continuous spectrum. The dark lines indicate the frequencies that have been absorbed by the atoms of the gas. The explanation of the hydrogen atom spectrum provided by Bohr's model was a brilliant achievement, which greatly stimulated progress towards the modern quantum theory. In 1922, Bohr was awarded Nobel Prize in Physics. De Broglie's explanation of Bohr's second postulate of quantization. Of all the postulates Bohr made in his model of the atom, perhaps the most puzzling is his second postulate. It states that the angular momentum of the electron orbiting around the nucleus is quantized, that is, lane equals nh, 2 pi, n equals 1, 2, 3. Why should the angular momentum have only those values that are integral multiples of h, 2 pi? The French physicist Louis de Broglie explained this puzzle in 1923, 10 years after Bohr proposed his model. We studied, in Chapter 11, about the de Broglie's hypothesis that material particles, such as electrons, also have a wave nature. C.J. Davison and L.H. Germer later experimentally verified the wave nature of electrons in 1927. Louis de Broglie argued that the electron in its circular orbit, as proposed by Bohr, must be seen as a particle wave. In analogy to waves traveling on a string, particle waves too can lead to standing waves under resonant conditions. From Chapter 14 of Class 11 Physics textbook, we know that when a string is plucked, a vast number of wavelengths are excited. However, only those wavelengths survive which have nodes at the ends and form the standing wave in the string. It means that in a string, standing waves are formed when the total distance traveled by a wave down the string and back is one wavelength, two wavelengths, or any integral number of wavelengths. Waves with other wavelengths interfere with themselves upon reflection and their amplitudes quickly drop to zero. For an electron moving in north circular orbit of radius Rn, the total distance is the circumference of the orbit, 2 pi Rn. Thus we have the equation 12.12. Figure 12.8 illustrates a standing particle wave on a circular orbit for n equals 4, that is 2 pi r equals 4 lambda, where lambda is the de Broglie wavelength of the electron moving in north orbit. From Chapter 11, we have lambda equals h by p, where p is the magnitude of the electron's momentum. If the speed of the electron is much less than the speed of light, the momentum is mvn. Thus, lambda equals h by mvn. From equation 12.12, we have 2 pi Rn equals nh by mvn or mvn Rn equals nh by 2 pi. This is the quantum condition proposed by Bohr for the angular momentum of the electron, equation 12.15. In section 12.5, we saw that this equation is the basis of explaining the discrete orbits and energy levels in hydrogen atom. Thus de Broglie hypothesis provided an explanation for Bohr's second postulate for the quantization of angular momentum of the orbiting electron. The quantized electron orbits and energy states are due to the wave nature of the electron, and only resonant standing waves can persist. Bohr's model, involving classical trajectory picture, planet-like electron orbiting the nucleus, correctly predicts the gross features of the hydrogenic atoms asterisk, in particular, the frequencies of the radiation emitted or selectively absorbed. This model, however, has many limitations. Some are: the Bohr model is applicable to hydrogenic atoms. It cannot be extended even to mere 2-electron atoms such as helium. The analysis of atoms with more than one electron was attempted on the lines of Bohr's model for hydrogenic atoms but did not meet with any success. Difficulty lies in the fact that each electron interacts not only with the positively charged nucleus but also with all other electrons. The formulation of Bohr model involves electrical force between positively charged nucleus and electron. It does not include the electrical forces between electrons which necessarily appear in multi-electron atoms. While the Bohr's model correctly predicts the frequencies of the light emitted by hydrogenic atoms, the model is unable to explain the relative intensities of the frequencies in the spectrum. In emission spectrum of hydrogen, some of the visible frequencies have weak intensity, others strong. Why? Experimental observations depict that some transitions are more favored than others. Bohr's model is unable to account for the intensity variations. Bohr's model presents an elegant picture of an atom and cannot be generalized to complex atoms. For complex atoms we have to use a new and radical theory based on quantum mechanics, which provides a more complete picture of the atomic structure.
This is why you need to know how the atom stopped being a blur and started behaving like clockwork. It's the leap from scattering gold to quantized orbits. Stick around. Bohr cleans up the mess. Back then, 1911, Ernest Rutherford fired alpha particles at gold foil and watched them bounce like tiny cannonballs off something hard at the center. He proved atoms weren't smooth blobs. They had a dense nucleus. But Rutherford's picture left a problem. Electrons circling a nucleus should radiate energy and spiral in. So why don't atoms collapse? Now enter Niels Bohr, 1913, with a bold fix. Bohr said, electrons occupy specific energy levels or orbits and don't emit energy while staying put. Jump an electron up. It absorbs a fixed quantum of energy. Fall back down. It emits a photon of a precise color. That simple idea explained hydrogen's spectral lines and made atoms predictable. Then, a nucleus scattered electrons, confusing and unstable. Now, clean orbits. Now, quantized jumps. Now, light explained by energy steps. Bohr didn't have the full quantum mechanics story, but his postulates were the bridge from classical chaos to quantum order. So next time you see a laser or a neon sign, thank Bohr. He turned Rutherford's puzzle into a rule book for atomic behavior. Science, hammer, then polish. That's your quick atom evolution. Rutherford's reveal, Bohr's rules.